In this video, we are going to look at topic 3.3, solids, liquids, and gases. The objective for this topic is to represent the differences between solid, liquid, and gas phases using a particulate level model. So these are going to be a lot of things that are reviewed from your previous chemistry class, but it's going to give us a good refresher before we move on. So first up, solids. Particles cannot change their relative positions in a solid. So solids have regular repeating patterns. Within those patterns, the particles can vibrate, so they can move back and forth just a little bit. Sometimes they can rotate, but they're not going to move any other than that. Their macroscopic properties are a result of their internal structure. So what makes up those solids, whether they're ionic, molecular, network covalent, that is what's going to determine their properties. The smallest repeating unit in a solid is called a unit cell. They are symmetrical. So when we look at the smallest unit, it's going to be symmetrical, and it's going to combine to form what's called a crystal lattice. And the crystal lattice structure can be determined experimentally via something called X-ray crystallography. So we can actually mathematically and experimentally determine the crystal structure of a solid. So we're going to briefly review our types of solids. So first we have ionic solids. So the formula for the compound is going to reflect the unit cell. So that's why you don't talk about ionic molecules, because it's a repeating pattern. It's a repeating network, essentially, of that unit cell. So the unit cell is going to contain whatever our formula says. So if we have, for example, lithium chloride, so Li plus and Cl minus, that ratio is going to be represented in the unit cell. We have molecular solids, which are molecular compounds packed into a regular 3D lattice to maximize the intermolecular forces. We have network solids, which are made up of entirely covalently bonded atoms. We have amorphous solids, which have no regular structure and therefore no regular properties. And then next, we're moving on to liquids. So in a liquid, the particles we consider them still packed tightly, but they're not held in place like they are in solids. The particles are held together by the intermolecular forces, and there's essentially very little volume change when you move from a liquid to a solid or a solid to a liquid, water being one of our main exceptions to that. And our particles stay in relatively close contact. And then finally, we have gases, and gases are governed by our kinetic molecular theory, or KMT. Our kinetic molecular theory tells us that our gas particles are in continual, rapid, random motion. So they're moving all the time, very quickly, very randomly. The space between the particles is so much bigger than compared to the actual size of the particles. What this means is that we can ignore the amount of space that the particles themselves occupy. And we can say the volume of the whole thing is the volume of the gas. So we can make some generalizations with that. It also says that kinetic energy is proportional to the temperature. So the higher the temperature, the greater the average kinetic energy. And then when our particles collide, because they're going to collide, there is no energy transfer. So they're perfectly elastic collisions is what we call them. So there's no energy lost or gained when collisions happen. When we talk about gases, we often measure pressure. And so that's actually what we're going to look at next. And so our pressure is affected by the number of particles, the volume, and the temperature. So gases, unlike liquids and solids, occupy no definite volume or shape. They can be compressed into any container. They can be forced to take up almost whatever space you want, and they take the shape of whatever container they're in. So liquids don't have a definite shape, but they do have a definite volume. You can't compress them. And then solids are going to hold their shape and their volume. Gases, they don't hold either. So when we're talking about those things changing, we're looking at pressure. So we're going to look at how pressure is affected by our number of particles, our volume, and our temperature. So that gives us a brief overview of what's going on at the particle level for our three states of matter.